Welcome to the Art of Counting, an exploration into the world of number theory. The study of numbers, an area of mathematics now known as number theory, dates back to antiquity. Through the intervening millennia, creative and curious people around the world have pondered the meaning and nuance of numbers. Today, number theory is one of the exciting and active branches of modern mathematics that has seen great breakthroughs, such as Fermat's last theorem, great applications, such as public key cryptography, and great open questions, such as the Riemann hypothesis, a complete and correct proof of which would entitle its author to a $1 million prize. In this course, we'll begin at the very beginning and delve into the basic structure of numbers, and then move into the study of surprising and stimulating results that have both tickled and confounded humankind for thousands of years. Beyond the ticker tape of numbers that possess clear and elegant patterns, we'll explore the enigmatic prime numbers. We'll discover the synergy between rational and irrational numbers. We'll visit the world of algebraic and transcendental numbers. And we'll journey into several modern areas, including elliptic curves, a critical key to unlocking the proof of Fermat's last theorem over 350 years of work. While some mathematical confidence would be helpful for our lectures, we'll always paint a big picture of the main ideas in an accessible and non-technical fashion before celebrating the intriguing and delicate details. In this opening lecture, we'll take our first steps into the abstract world of number theory and see how it fits in within the larger mathematical landscape. We'll come to view mathematics as a living and growing intellectual pursuit, and mathematicians as both artists creating new worlds and as explorers attempting to build better understanding of our universe. Throughout their scholarly journey, mathematicians navigate through the subtle and narrow confines of truth. Mathematicians create conjectures, which is really just highbrow verbiage for educated guesses. These conjectures are either proven to be true, in which case they're awarded the title theorem, or a counterexample is discovered, demonstrating that the conjecture, in its generality, is actually false. If true, then the mathematical mind asks if the result can be extended or generalized. If false, the mathematician wonders if the statement can be salvaged. That's how the frontiers move forward. Here we'll describe this intellectual exploration and how it allows the frontiers of mathematical knowledge to genuinely move forward. Number theory is one of the oldest and most important branches of mathematics. At its very essence, number theory is the study of the natural numbers, the numbers 1, 2, 3, 4, and so on. More precisely, it is an intellectual discipline concerned with the arithmetical structure of the natural numbers and the extensions and generalizations of these numbers. Now, while many people may believe that all of mathematics is understood, in this course, we'll see that mathematics in general, and number theory in particular, are ever-evolving works in progress. And, just as with other artistic pursuits, are driven by the fashion and tastes of today's practitioners. In this lecture, we'll offer a window into the mathematical culture and then introduce some of the main branches of number theory, foreshadowing our journey ahead. After this overview of number theoretic ideas that we'll encounter throughout our course, I thought we'd close with a proof of our first mathematical truth, the whimsical theorem, if you will, asserting that every natural number is, in fact, interesting. Well, as we enter the world of numbers, we first consider the motivation for number theory. We begin with the counting numbers, which we call the natural numbers. They're the numbers 1, 2, 3, 4, and so forth, and they'll follow us throughout our entire journey. Now, numbers slowly evolved from useful tools to objects of independent interest. Now, if you think about it, numbers at the beginning were used to describe things. They were adjectives. We have 5 apples. We have 10 sheep. But soon, humankind and the human imagination was captured, and one isolated this adjective and turned it into a noun, the number 3 or the number 10. And once it became a noun, it became an object of curiosity and an object of study. Now, the true motivation behind the theory of numbers comes from a desire to study the simplest numbers, these natural numbers. One of the fundamental recurring themes throughout our entire course is that when we explore simple objects with great depth, we uncover otherwise invisible, delicate structure. And we'll see this again and again. Now, there are many different types of numbers that we'll see throughout our course, and I wanted to quickly introduce you to them, although we'll see them in greater depth as we go. The natural numbers, of course, are the numbers 1, 2, 3, 4, and so on. The integers are the natural numbers together with their negatives and with 0. So 1, 2, 3, 4, and so on, together with -1, -2, -3, and so on, and we also toss in 0. Those are the integers. The ratios of integers, which we can think of as fractions, are called the rational numbers. The numbers that are not ratios are called irrational numbers, numbers without ratio, so to speak. And these confounded mathematicians way back into the ancient Greek time of Pythagoras, as we'll see. The decimal numbers are called the real numbers and can be viewed as points on a number line from our youth, or the numbers that pop up when we use a calculator and see the decimal point and lots of digits. Well, once we identify different types of numbers, they do genuinely take on a life of their own, dictated by the laws of nature and mathematics. Much of the journey ahead, in fact, is a thorough study of their rich and intricate personalities. And I'll actually refer to numbers as having personalities, although we'll mean that in a mathematical context. In fact, we'll see many surprising connections between these different types of numbers. This interplay and synergy between numbers will be another recurring theme throughout our course. Well, before moving on, I wanted us to take a moment to reflect upon the broader culture of mathematics. Mathematics is an ever-growing area of active research. Mathematics is an abstract universe of both nature and the mind. For example, we see objects moving in our everyday lives, we see the motion of planets, and now understand motion through the abstract ideas of calculus, the study of change. We see shapes and we wish to describe them, and this leads us to the abstract universe of geometry. We see quantities of objects and we count, and this leads us to the abstract world of number theory. Mathematicians are at once explorers and artists. We see the world and we try to capture, not on canvas what we see, but we try to capture it through mathematical formulas and theorems. Mathematics is a search for structure. When we see pattern in our world, that is often a sign that in fact there's some underlying structure at work. So our quest in mathematics is to identify this underlying structure that explains the patterns we see. Once we develop the structures and explain the patterns in the real world, we often find new abstract structures and patterns within the mathematics itself, which may have obvious connections with our original inspiration. I now want to say a word about how we move the frontiers of mathematics forward. First and foremost, mathematics, and most of mathematics, in fact, has not yet been discovered, and even more is not totally understood. Mathematics is difficult, first of all, and creating new mathematics is, in fact, particularly challenging. Mathematicians, as a community, build on each other's works to move the boundaries of understanding outward. The discipline of mathematics rests upon the foundations of a handful of basic self-evident truths known as axioms, and then rises up from there. We study simple objects or phenomena and search for patterns. Now, the patterns that we discover lead to our conjectures, which in turn, in the best of all possible worlds, lead to new theorems. Well, once a new theorem is discovered and a rigorous mathematical proof is created, the work is submitted to a scholarly journal, and the mathematics community reviews the work, usually by sending it out to anonymous referees who are also experts in the area. And if the work is correct and complete and of sufficient interest, then it is accepted into the journal and it's accepted by the community, and the new results are deemed a theorem. Thus, in the final analysis, the pillars of mathematics are the rigorous proofs. So what's a rigorous proof? Well, a rigorous proof really is just a string of declarative assertions, each deduced from the one before. So in some sense, mathematicians are at once artists and lawyers. We're trying to create an argument. But unlike the lawyer who, for whom guilt and innocence is rest on a reasonable doubt, here there is no reasonable doubt. It has to be ironclad. Our course will continually celebrate the creativity involved in constructing a rigorous proof. And we'll actually see rigorous proofs for ourselves and construct them and create them, and we'll appreciate the creativity involved that much more. Well, stepping back now from the panoramic view of all of mathematics, we now focus on the question, what is number theory? Well, the two main branches from which most of the questions of number theory fall are known as analytic and algebraic number theory. Analytic number theory focuses on the primes. Now, the prime numbers, which we'll say much more about in future lectures, are those natural numbers greater than 1 that cannot be written as the product of two smaller natural numbers. So, for example, the first few prime numbers are 2, 3, 5, 7, 11, 13, 17. They can't be broken down into smaller parts by multiplication. 6, however, is not a prime because 6, notice, can be written as 2 times 3, two smaller natural numbers. We'll study Euclid's insight that the prime numbers form the building blocks for all natural numbers. In particular, every natural number greater than 1 is a product of prime numbers. Well, are there infinitely many prime numbers? Euclid answered this question, and his proof is considered to be one of the most elegant arguments in all of mathematics, and we'll see this for ourselves. Refining the issue of the infinitude of primes, mathematics wondered about the proportion of natural numbers that are prime. As we'll see, this inquiry led to the discovery of what's called the prime number theorem, proved in 1896. The prime number theorem gives an approximation to how many primes we have up to any particular point. Now, one of the most important open questions in mathematics asks how good this approximation truly is. In its precise form, this question is now known as the Riemann hypothesis and remains one of the most important open questions in all of mathematics. This area of number theory is known as analytic number theory because it often employs the techniques of calculus to establish the truth of its results. Now remember, calculus, let me just remind you, is the study of growth, the study of change, the study of movement. So studying the growth of primes using the mathematical study of growth seems appropriate. And the techniques, in fact, of calculus are used, and therefore it's called analytic number theory, because the area of mathematics within which calculus resides is known as analysis. Algebraic number theory, on the other hand, has its focus on arithmetic. Here we'll take a look at equations that just involve addition, subtraction, and multiplication of natural numbers. And the most basic question we can ask is, can we always find natural numbers that are solutions? Namely, natural numbers that will satisfy the equation or make the equation true. Such equations are called Diophantine equations, named after the great Greek mathematician Diophantus of Alexandria. For example, if we consider the equation that arises from the Pythagorean theorem that equation that we saw quite a while ago in our grade school days, x squared plus y squared equals z squared. Remember that x squared just means x times x. Then we see that if x takes on the value 3, if y equals 4, and z equals 5, well, these are natural numbers, and notice they satisfy this equation. For if we take 3 and we square it, that's 3 times 3, that gives us 9. If we take 4 and we square it, that's 4 times 4, that's 16. And 9 plus 16 is 25, which notice is indeed 5 squared. So we have a solution. And in fact, a solution where all the unknowns are natural numbers. Well, are there other solutions? Are there infinitely many? These are the questions that we face. As we'll see, the famous Fermat's last theorem states that a generalized version of the Pythagorean equation has no natural number solutions. Finding a complete proof of this assertion remained one of the most prized open questions in mathematics for over 350 years, until it was finally established in the mid-1990s, which actually indicates and provides us with a wonderful life lesson that number theory in mathematics teaches us, which is that we should really always be very, very tenacious and never give up. Tenacity is quite often the best way to combat difficult, challenging issues. Never, never give up, because in fact, the solution might be right around the corner. And we'll see this theme occurring in our course. The study of solutions to equations, of types of equations, will actually lead us to discover a generalized notion of integers, and in turn, a generalization of the prime numbers. Well, because this area of number theory is inspired by a search for solutions to equations, it is known as algebraic number theory, because we use the algebra that we're used to seeing from our youth to look at solutions. Given that both analytic and algebraic number theory involve the study of primes and their generalizations, it will not be surprising to discover an important interplay between these two branches of the theory of numbers, and we'll see that interplay for ourselves. Well, now I want to offer a few vignette scenes of the vistas ahead in our journey through number. We'll open with an excursion into elementary number theory. Now, elementary here in mathematics doesn't mean easy. It means that the questions can be posed and can be understood by many people, and the solutions don't involve very advanced mathematics, but instead a very clever coupling of ideas together. We'll discover some interesting patterns involving the natural numbers. Now, these attractive patterns not only hold an independent aesthetic appeal, but are also extremely important tools required to understand the deeper ideas of number theory to come. So we'll be building the foundations. In addition, these early expeditions into pattern will provide us with the opportunity to create our own conjectures and to gently introduce us to the world of rigorous proof. In some sense, we'll enter the world of rigorous proof at the shallow end and slowly move into the deeper, more interesting end of the number theory pool. Well, we'll then turn to analytic number theory, and here we'll formally introduce the prime numbers and study their central role in the universe of number. Next, we'll see a different method of calculation known as modular arithmetic. Modular arithmetic is really nothing more than clock arithmetic. For example, if we add 3 hours to 11 o'clock, our clock would show 2 o'clock. So we somehow came around after 12 and started over again. This is the arithmetic of cycles. Combining the properties of primes with the clock arithmetic that we'll develop, we'll discover a world of arithmetic involving division that focuses on remainders rather than quotients. As we'll see, this classical study holds one of the most important modern applications of number theory: public key cryptography, which is the fundamental and foundational feature that occurs in all modern digital communication. We use it all the time. This will naturally bring us to algebraic number theory, whereby searching for simple solutions to certain equations, we'll come upon parallel universes of number that will cause us to rethink the basic arithmetic and mathematics that we were taught in school. Next, we'll see the potent combination of algebra and geometry as we explore the modern area known as algebraic geometry. Here we'll discover an important connection between solutions to certain equations and points on certain curves. The interplay between number theory and geometry is one of the most profound areas of current research in number theory today. We'll then move to the mysterious world of algebraic and transcendental numbers. Here we'll wonder if there are numbers beyond those that are the solutions to the equations we considered in algebraic number theory. And we'll see the answer is yes. This issue remained unresolved for thousands of years until the definitive answer was finally found in the mid-1800s, which in the scope of mathematical history was essentially yesterday. We'll then close the course by considering how we can represent numbers. Beyond writing numbers as familiar decimals, we'll discover an alternative manner to express numbers that is much more sympathetic to number theory inquiries. This manner of expanding numbers allows us to build insights into many phenomena, from why 22/7 so closely approximates the number pi, and then extends to why we have a 12-note chromatic musical scale. So we'll see many features that come clear by just looking at how we represent things. Throughout the course, we'll offer applications and stories both famous and whimsical that will not only enhance the number theory at hand, but will provide a context within which we can better appreciate our discoveries within the world of number. Well, before closing this introduction, I wanted to make a few personal remarks. Now, I'm a number theorist, and therefore I'm particularly excited about the prospect of sharing this incredible universe of number with you. So in my research, I'm actually proving new theorems in number theory, and so this is something that's near and dear to my heart. Number theory, in fact, really is indeed one of my intellectual passions. For one thing, the questions are often very easy to pose, and yet the questions involve answers that might elude humanity for thousands of years. I believe that numbers are intriguing objects of nature and our imagination. They're at once basic and profound. I'm also drawn to the creativity and originality involved in crafting arguments. That is, rigorous proofs that we'll see again and again. The proofs that we'll see throughout our course, in fact, will together paint an abstract portrait of beauty and detail. Now, there will be moments of technical detail, some of which will have algebraic components. Now, there's a wonderful quote due to my late friend, the 20th century mathematician Giancarlo Rota, who spent most of his career at MIT. And here's what he said about mathematics. A mathematician's work is mostly a tangle of guesswork, analogy, wishful thinking, and frustration. And proof, far from being the core of discovery, is more often than not a way of making sure that our minds are not playing tricks on us. So a wonderful quote that really captures the spirit of what we do in mathematics. Number theory can be frustrating, but I urge you not to get bogged down in the details if that's not of interest to you. Instead, I urge you to take it all in at once and let the ideas leave you with an impressionistic sense of the arguments. In fact, I propose that we should view mathematical proofs as a style of art, perhaps a style with which many are not familiar. When we first look upon the works, they look jumbled, confusing, abstract, and challenge our senses. I urge you to stay the course. Just as with any new type of art, we can only appreciate the style once we've had a chance to see many examples and know where to look and what to see. So please think of me as your number theory museum curator. Well, I thought that we should really leave the lecture, this first lecture, this opening lecture, by actually proving something. And I thought that we should prove a theorem that captures the spirit of what we are going to be looking at for the rest of the lectures, even though it is a little bit whimsical. And the theorem is, every natural number is interesting. Well, how would you prove something like this? Well, the proof of this whimsical assertion actually illustrates a style of argument known as proof by contradiction. Here we actually will assume the opposite of what we hope to prove and hope to deduce something that's just totally false, thereby contradicting ourselves and thus showing that our assumption was genuinely false. Okay, so now let's take a look at why every natural number is interesting. So we consider the first natural number, which is the number, of course, 1. Now, it's the smallest natural number, and thus that's certainly interesting. It's the first one, that's certainly interesting, so 1 is interesting. Now, the next natural number is 2, and notice that's the smallest even natural number, which is certainly interesting. Also, by the way, 2 is the first prime number, which is really interesting. So we see that both 1 and 2 are indeed interesting. Okay. Now, could there be a natural number that is not interesting? Well, if so, then there must be a smallest such number. That is, the smallest natural number that is not interesting. In other words, every natural number less than this one is interesting, and this number is the first natural number that is not interesting. Well, isn't that interesting? So the point is that if you think you have the smallest natural number that's not interesting, then since it's the first one, that automatically means it's interesting. Well, that shows us that we never have a number that's not interesting because, in fact, whenever we have one, the first one would be interesting and it skyrockets from there. Well, this exclamation concludes our humorous proof. But it really does illustrate something important. The world of number theory is indeed interesting, and every number is worthy of exploration. Our journey ahead is teeming with deep ideas, profound insights, and incredible discoveries. I'm delighted we'll share the world of number theory together.